First of all, thank you very much, Rito, for the invitation. It's a great pleasure to be here. And what my talk will be about is essentially some fairly recent work that I've done, which I think could be fairly useful in the space of kind of climate, weather, where we're kind of used to using very expensive simulations. Now, I'm not actually going to talk about weather or climate, but I'm going to talk about another type of, or maybe a very specific subset of that. So with some connection with tsunami modeling, which we've talked about. There's also going to be quite a few connections with a few of the other talks, and so I'll put some kind of pointers to how the work connects. The work is all based, or the talk is all based on this paper, which appeared this year at AI Stats. And it's in collaboration with a bunch of colleagues at UCL, including Serge and Dan, who are kind of resident tsunami experts, and we've kind of heard about them already, and Toni Karvonen from Helsinki University. And the work was led by Kaiju Lee, who was a PhD student with Serge and I. Right. So the kind of topic of this talk is going to be how to tackle numerical tasks. And specifically, it's going to be about tackling integration problems. So just to kind of settle the notation, I'm going to have some function f. And my goal throughout this talk is going to calculate the expectation of this function f, or in other words, its integral, against some distribution pi. Okay, and so the domain of the function will be something like RD or a subset of that, and the function is real valued. Now, of course, you know, especially here at Warwick in the stats department, you know, it's really one of the strongholds of Monte Carlo methods. So this should be fairly obvious, but the kind of easiest way to kind of approximate an integral like this would be through Monte Carlo methods. So the very simplest thing you could do is just simulate from pi, and then use your samples to create an estimator, which is just some sort of equally weighted sum to estimate that integral. Now, of course, there's various variants of this that can make it more efficient. You can, you know, try to weight the samples. You could try to do something specific if your problem is high dimensional, et cetera, et cetera. Or in cases where you don't know how to sample from pi, you might go around that by using some sort of Markov chain. Now, the problem with this is that a lot of the time, especially in these sorts of kind of climate, weather cases, your samples might be something very, very expensive. And I insist on the very, very, not just very, just twice very, because that's very often the case, at least relative to the cost of calculating the integral. And so that's going to create problems for pretty much any Monte Carlo method. So even if you use these slightly more advanced methods that, you know, use some more properties that might converge a bit faster, you're going to start having some challenges if your problem is very expensive, and hence n is going to have to be quite small. So just to give two examples, the first one is something that I'm not actually going to talk about, but you'll see in Andrew's talk just after, is imagine if I had to calculate something like the expected energy produced by a given wind farm. Now, one thing I could do would be to kind of build some sort of computational fluid dynamic model of my wind farm, do some simulations for various parameter values. So maybe my expectation is over some distribution of wind directions, let's say. So I'd have to sample lots and lots of times, which in this case would be running this model lots and lots of times. And if my model takes, you know, a substantial amount of time to run, then, you know, my estimate of this expected value might be quite challenging to calculate. And so Andrew's not going to talk about expectations, but he's going to talk about this model in the next talk. Another example, which I'll actually talk about in this talk, is tsunami modeling. And we've heard about tsunami modeling already. So here, the very simple kind of integral that I'm going to calculate is essentially the expected intensity of a wave when it arrives at this point, where my colleague Serge is having some good time, given there's been a tsunami generated by some sort of landslide. Now, typically, and we heard about that yesterday, we don't know everything about how that tsunami was generated. So in this particular case, it's a landslide-generated tsunami, so you might not know things like, how much mass fell, what's the slope, various things like this. So you might have some uncertainty about these. You can go and talk to some scientists. They might give you some distribution about these, for these. And what you might want to know is, let's say, what's the expected intensity of the wave when it arrives here, given at a certain point in time, given some uncertainty I have about these parameters. Now, in this very simple toy tsunami model, it takes about 3 minutes to kind of simulate one of these tsunami waves. And that's really like a very simple model. Now, if I want to, calculate the expected intensity of the wave here, that's going to be way too expensive, because if I have to do these 3-minute simulations, okay, I might be able to do them in parallel, but if I need, tens of thousands of them, that might be a bit late to then let Serge know that, he should really move from where he is. And so the kind of problems that I'm interested in this particular talk is these sorts of really expensive cases where simulating is expensive, and so you have to be a bit careful with how you use your simulations. So in summary, the sorts of problems that I'll look at will typically have a fairly small number of observations n, and I can usually expect a fairly significant numerical error to remain even after I've run whatever algorithm I'm going to use. And so what we need to do to tackle, or one thing we could do to tackle this problem is to try to make more use of the structure of the particular integration problem we're going to look at. And so what I'll talk about is one way in which you can do this. The other thing we might need is, given there's going to be significant numerical error, is to try to quantify this error. And so I guess Marvin's already talked about, quantification of uncertainty in the case of numerical tasks yesterday. And here, this is going to be yet another example, but in the case of integration. Okay, so what I'll do first, so my kind of, the title of the method is called Multilevel Bayesian Quadrature. So I'll first talk a bit about multilevel and multi-fidelity methods. So this might be familiar to those of you that know about multilevel Monte Carlo. And essentially, if you do know about multilevel Monte Carlo, you can think of our method as an extension of that line of work. And if you don't know about it, that's fine, because I'm just about to explain it. Okay, so in kind of multi-fidelity models, what I typically have is not just one function that I want to integrate, but I might have a sequence of functions, f0, let's say f0 to fl minus 1, which are all approximations of that function f. Now, they're approximations such that as I go along this sequence, my approximations become more and more accurate, but also more and more expensive to evaluate. So in the case of, let's say, the tsunami, the way you can think of it is, in practice, for me to run my tsunami, I need to solve some PDEs. I might do this, very accurately with a very good solver, or less accurately with a worse solver, and that might give me, let's say, 2 versions of, or 2 elements in this sequence. Okay, but potentially I could have up to L of them. And so I'm going to write my F, the one I actually care about integrating, as FL. So it's essentially the end of this sequence, the most accurate. Now, the very kind of simple trick that multi-level Monte Carlo uses is the following trick. So I have my integral of F, and that's the same as F of L, FL, because just by definition. So what I can do is simply add and subtract and then add it back each of the elements of this sequence. So I'm going to first subtract FL minus 1, add it back, subtract FL minus 2, add it back, etc., all the way to the bottom. Now, here what I've done is I've color-coded each of these terms in different colors. And if I hadn't done that, you might think, well, what's the point of me adding and subtracting things? Well, the point is that each of these integrands, so the kind of quantities that could be integrated, is going to change in terms of the computational cost that it's going to have. So here at the very top, because I have to evaluate both this and this, if I'm going to try to estimate this integral, this is going to be very expensive. If I go all the way to the bottom, this is going to be very cheap. Right? So I've kind of turned my one integration problem in terms of a sum of integration problems of varying cost. And that's called doing a telescoping sum. Now, what multi-level Monte Carlo does, and it's an algorithm which has existed for a very long time, I think at the very least since the 2000s. There's a nice kind of review paper in Acta Numerica in 2015. Is it basically uses Monte Carlo to estimate each of these terms. Now, why is that a good idea? Well, the reason it's a good idea is that I don't need to use the same number of function evaluations for each of these Monte Carlo estimators. So in particular, for this term, because F0 is cheap, I can just use a very, very large number of evaluations of F0s. But potentially, I can use only a few of evaluations at the most expensive level over here. OK. So what people normally do is they try to optimize the way in which they allocate their computational budget. So here, I'm going to have this vector, n MLMC, which is going to be the best possible way to allocate my computational budget across each of these levels. So it's going to be essentially the number of times I'm going to evaluate the integrand in each of these terms. And with fairly simple derivation, what you can show, and this is shown in this Acta Numerica paper that I mentioned just before, is that the optimal way to allocate your budget is as follows. So at level L, small l, I'm going to allocate my budget according to the ratio of VL and CL to some power, where VL is the variance, the variance at the ELF level, and CL is the cost of evaluating at the ELF level. So why does that make sense? Well, the reason it makes sense is that obviously the more expensive something is, the less often you would like to evaluate it. At least intuitively, that kind of makes sense. And here, this variance term essentially tells you how hard is this particular integration problem for my Monte Carlo method. So if this variance term is very small, then that means that I have an easy problem. And so I might want to evaluate less often. But if this term is very large, then I might want to evaluate a lot more often. Now, the kind of key thing to note is that FL and FL minus ones are both approximations of the same thing, and they're getting more and more accurate. So in particular, you could expect that at least for the high levels, this is going to be very close to 0, right? Because you have two approximations of one thing, and they're both very good. So when you subtract them, you should be around 0. And hence the variance of 0, or let's say the constant 0 is, of course, 0. Now, of course, in practice, it won't be exactly 0, but it'll be roughly there. And so that's why VL will typically be small for the highest levels. But of course, CL will be large. OK. This is all very nice. But multi-level Monte Carlo as such doesn't really use any structure of the integrand. So you might know lots of things about your integrand that you might want to use to improve on this. So for example, if you know, I don't know, your function is periodic, then you might want to encode that into your estimator. If you know it has a certain level of smoothness, again, you might want to add it, or perhaps even sparsity. And there's a huge range of extensions of multi-level Monte Carlo which do small variations on this, but many of them can't really, or don't quite build that much structure into the method. And so I'm not going to talk about these, but I'm going to talk about another approach that we used to extend multi-level Monte Carlo, and it'll be in a very similar line of thought that from the talk that Marvin gave yesterday. Okay. So multi-level Bayesian quadrature. So the idea is going to be combine Bayesian emulators with multi-level Monte Carlo. Now, why Bayesian emulators? Well, we've talked already about how they can be quite useful to kind of encode knowledge we have about problems. I guess in this sphere, people are also quite used to using Bayesian emulators, so it's quite a natural thing. So when I first started talking with Serge about this problem, he already uses emulators for these tsunami problems all the time. And so for him, it was a very natural thing to try to use these emulators as well to compute not just to do regression or kind of interpolation, but also calculate integrals. So how can I do this? Well, it's really trivial. And so the method is extremely simple. I'm just going to do this telescoping sum, and I'm going to replace the Monte Carlo estimators at each of these levels with this other method called Bayesian quadrature, which is based on these emulators. And I'll explain how it works in a second. But that's all. Like, the method is extremely simple. Now, Bayesian quadrature has existed for a very long time. So there's these kind of classical now papers by Diaconis and Tony O'Hagan from the kind of late 80s, 90s. And there's also this more recent paper that I wrote where you can see some sort of overview of the method if you're interested. Okay, so how does it work? Well, I'm just going to explain it with a picture just to give you some intuition. I'll put some formulas in the next slide, but just to give you some intuition first. So imagine that this red curve is my integrand f, the one I want to, the quantity I want to integrate. So what I'm going to do is I'm going to place a prior distribution on this function. Now, I'm going to use Gaussian processes. You don't really need to do this, but it's kind of the most convenient thing to do for various reasons, mostly computational, but also kind of placing priors that are Gaussian processes is a lot simpler than other things. So let's say I'm going to put a Gaussian process. So this is going to be my mean, and this is some region which tells me 95% credible areas. Now, I can simply do Gaussian process, not regression, but here interpolation. So I can get some data about this function. I can simulate from my tsunami model, evaluate my function, get some data. As I get more and more data, you have these usual plots where I get a more and more concentrated posterior on the function. But what you also get for free, if you're a bit careful, is a distribution on the value of the integral. Why? Well, because integration is just a linear operation. And if you know about Gaussians, you know that the great thing about Gaussians is that whenever you apply a linear operation on them, you still keep a Gaussian. So in this particular case, if I integrate, I'm going to end up with a univariate Gaussian distribution on the value of the integral. And so here, the true value is this dotted line. I have a Gaussian, which is at the start going to be extremely flat because I haven't evaluated. And as I evaluate more and more, I'm going to get a Gaussian, which is going to be much more concentrated. Okay. And so Bayesian quadrature is essentially this posterior distribution on the value of the integral, where the estimator is just the mean, but you also get some notion of uncertainty through the posterior variance. Okay, so what does that do on kind of the multi-level setting? So now I have another example. This very simple function f2. It's just this quadratic-like curve here. I have a bunch of approximations of it, which are these kind of piecewise linear approximations. Now, if f2 is very expensive, and let's say I can only evaluate it 4 times, like here, I'm going to get a really, inaccurate approximations of f2 because, well, I only have 4 data points, and so I can't really expect it to do so well. I'm going to have really high uncertainty. And if I look here at the value of the integral, so this is the truth, I have a very flat posterior because I'm very uncertain. I've only had 4 data points. Okay. Now, what multi-level Bayesian quadrature does is it's going to do Bayesian quadrature for each of these terms in this telescoping sum. And we're going to put a prior GP on each of these integrands. It's going to be fairly simple because all of them are differences of approximations of the same thing. So the mean is going to be 0. And we only need to be think a bit about the covariance function. So essentially what I can do is, evaluate a lot more often the cheap ones. So kind of hidden here behind my legend is lots of evaluations of f0 and therefore very accurate approximations. I have a few less evaluations of the difference between f1 and f0, and maybe only here 3 evaluations of the last level. But when I put all of these together, so if I sum a bunch of univariate Gaussians, I'll just get another univariate Gaussian. So once again, I get a posterior on the value of the integral, which this time is much more concentrated. And you can see this already in the approximation of f2. So if I just sum all of my GP approximations of these differences, I get something which is much more concentrated on the truth. And here, this is for the potentially for the same computational budget. Okay. So I think I might actually skip over the equations because they're not particularly interesting, and you've kind of seen Gaussian processes before. The kind of main thing is you typically have a fairly high cost compared to Monte Carlo because you're using GPs and they can be quite expensive. So usually you have these terms of these sorts of matrix inverses to calculate. Now you can do this in very clever ways, maybe to reduce this, but at least in the kind of dumbest setting, it's going to be n cube per level. So my total cost is going to be the sum of n cubes, where here I have NL because potentially I have different L's, n per level, which is much more than multi-level Monte Carlo. But maybe it doesn't really matter because, if it takes me a very long time to simulate my tsunami, and n cubed for n not that large is not going to be, it's going to be very negligible in this case. Okay, and there are things you could do to kind of further reduce it, which we did not do because it was really not necessary in our case. So we have some theory as well. I guess the theory, I didn't want to put like a big theorem with lots of assumptions. So at a high level, the sort of thing we need to assume are essentially smoothness of the function that we're trying to integrate. And this can be encoded through kind of Sobolev spaces. If you don't know what that is, just know that there's this parameter tau, which tells you something like the number of derivatives that my function will have. And so Sobolev spaces are just spaces of a certain smoothness. If you know what they are, then it's good. Everything else is fine. So what I'm going to need for my theory is things like my domain on which I'm integrating should be nice. Again, I'm skipping what that means. I should choose my points nicely. Again, I can skip. But kind of more crucially, I'm going to need my kernel at each level to have a certain level of smoothness. And also the true functions to have a certain level of smoothness. Now, these smoothness do not need to match, but your rate will be best if it does match. And what you can show is a bound on the numerical integration error. So here, pi of f is the quantity I'm trying to estimate. This is my estimator, so it's the mean that I get from this multi-level Bayesian quadrature. I can write a bound, which is essentially a sum. Each term is essentially a bound on each of these terms in this telescoping sum. And kind of crucially, the rate is going to be proportional to this quantity. So NL is the number of evaluations, tau L is how smooth the problem is, and D is the dimension. So in high dimensions, this method will be terrible. However, if you're in low to moderate dimensions, but you're very smooth, then this method will be awesome because this will go to 0 very, very fast. Now, typically, again, I need to make all of these terms in this sum essentially small to have a small bound overall. And I can play the same sort of game that multi-level Monte Carlo does. So what I can write is what's the optimal number of samples per level, but this time for multi-level Bayesian quadrature. Now, this time what I'm going to do is I'm going to go for like a fixed worst case error, so a fixed error from before, for a function of a certain smoothness. And what I can show is that the best allocation of budget is of this form. Now, here CL is again the cost. This thing is another way of measuring the complexity of my integration problem. Before I was using the variance, now I'm using this norm, which is the Sobolev norm, essentially some way of measuring kind of regularity of functions of a certain smoothness. And it should look very familiar because it's exactly the same form as before. So this was a multi-level Monte Carlo result. Essentially, I still have this CL at the bottom. I have a slightly different way of measuring regularity. And in fact, the variance, you can just write it also as a norm. It's just a norm in L2 as opposed to Sobolev norm. And a slightly different coefficient. But again, you can find, there's a way of determining how to allocate your computational budget. Now, how much time do I have? 5 more minutes? OK. So this is kind of a very baby toy model just to check how things are working. So this model is super simple. And the reason that we we kind of used it was just to check everything. So we can find the solutions of this problem in closed form. We can compute all the norms in closed form. We can do everything in closed form. So we just wanted to check that things worked OK on this. So what I'm plotting here is the absolute error for different computational budgets. So this will be, let's say I know that my total budget is 1.5 seconds in this particular case. Then I'm going to use my either multi-level Monte Carlo or multi-level Bayesian quadrature up until I reach that budget, and then I'm going to stop. And therefore, since I know what my budget is, I can try to allocate the points. OK, so the red histograms, sorry, box plots, are always multi-level Monte Carlo. And the green ones are a multi-level Bayesian quadrature using the same points as multi-level Monte Carlo. So here you can see that just using a slightly better estimator for this problem is already going to reduce significantly your error. Now, what I can also do is, in Bayesian quadrature, is use different kinds of points. So in Monte Carlo method, I'm kind of forced to use IID samples or some sort of version of that if you're using markup chains or something like that, but it's close to IID anyway. If I use GPs, I can basically put my points wherever I want. I could do experimental design, I could do all sorts of other things. So here I did something like that, but a really dumb thing. I just put a grid just to show you the difference. And so this time I only have one line because I can't repeat the experiment lots of time because the grid is fixed. So you see that already using something slightly better than IID points, I again get a huge gain. So I can get a huge gain by using a better estimator. I can get a huge gain by picking my points slightly differently. And here, at least in this particular experiment, we didn't get a huge gain from optimizing more how we allocate budget across levels. So we use the same allocation as multi-level Monte Carlo, and that was already fairly good. On the right-hand side, I have a kind of calibration plot. So this axis tells me essentially the uncertainty that I get on this estimate of the integral through multi-level Bayesian quadrature. So if I'm at 0.8, I expect, if I repeat the experiment, to have the truth be in this interval 0.8% of the time. And this is what happens for multi-level Bayesian quadrature for different computational budgets. Now, what you notice is that we tend to be on this side of, so the ideal would be to be on this line, and we tend to be a little bit above, which essentially means that we're being a bit pessimistic, i.e. Uncertainty is a bit larger than it needs to be, which is completely fine because it's better to be pessimistic than to be, very, very certain of a wrong answer. So we did the same thing with the tsunami model. And again, here are like two different quantities of interest that Serge wanted to calculate with our method. Here the problem is fairly low dimensional, so we're only in dimension 3. We know there's some smoothness, so we use a Matern kernel, and just using that, we get huge improvements in terms of accuracy. So like we can roughly, it's not quite 10, but it might be at least five times less to get a fixed level of accuracy. So that's it. So I guess I've exceeded my time. One thing to say is that the methods is evaluated in Problem, which Marvin is one of the lead author of. It's a Python library to implement these sorts of Bayesian numerical methods. Now, my conclusion is going to be that multi-level Monte Carlo is great, but sometimes kind of using Bayesian emulators for these really expensive simulations can be super helpful. So here I've shown you one way of doing this. One nice thing as well is that you get not just a point estimate, but an entire posterior distribution, and I had to skip a bit at the end, some more experiments on that. And the nice thing is that you can combine multi-level Monte Carlo methods with all sorts of other interesting kind of integration methods that you might have, so changing things like point sets, et cetera, et cetera. So you can find out more in this paper, and I'm very happy to chat with anyone that is interested in this. Thank you.
Thank you very much. Do you have, okay, I have the.
Yeah, thanks for the nice talk. What was the regularity of Z in your toy example?
I think it was very low. Did I put it on the slide?
You didn't.
So I cannot remember, but it was very low.
Okay.
Yes.
So probably some Brownian motion or something like that.
I believe so. Yes.
Okay. So is this method then competitive if you say use standard quadrature techniques? I mean.
So in this particular case, it would be not, because it's not an interesting problem to apply to. It was just to check that things work.
Sure. So you say this is an interesting problem for more complicated settings, but in this one-dimensional setting, it's probably
it would not be competitive at all. Yeah, for sure, because you can do much more clever things in this toy problem.
I was just interested.
So the reason that it might be helpful in more complex problems is some of these quadrature methods, they tend to be quite intensive in terms of things like point placements. So like if you start going to higher dimension, let's say, you might need to take like kind of products of grids and things like this, and then you have a lot of functional evaluations.
But then all this geometry really becomes very complex.
Exactly. Yeah. So then it starts becoming difficult. Yeah. In this problem, it would probably work better. Yeah.
Super. Thanks.
Thank you very much. Is there other questions? Okay.
Actually, I'll ask a similar question as yesterday. So I'm always worried with these kind of methods with Gaussian processes that in the end you use MLE for the hyperparameters and you're ignoring the uncertainty there. And let's say you're unlucky with the points you choose and the function looks constant from the points you choose, actually is not constant at all. And basically with the hyperparameter tuning, you're going to ignore the uncertainty there. And so are you worried about kind of failure points with these kind of issues?
Yeah, so it can definitely be a problem. That's actually something that I'm working on kind of separately, kind of parameter estimation for Gaussian processes generally. It can be a problem here. What I would say is that there's a few things you could do if you wanted to avoid that issue. You could kind of estimate hyperparameters in different ways. So you could do like a hierarchical model. Now, the reason that wouldn't be so convenient is that essentially, if you did that, you would lose the whole kind of conjugacy of the Gaussian process, which means that then I would need to put a lot of effort into kind of computing the posterior distribution on the value of the integral. I could do it, but it would be like essentially it would be like, using a Bayesian method where I need to do lots of complicated computation to solve a computation problem. Now, that might still be cheaper to do. So it might still be worth it if you're like in really expensive problems. But I guess for most cases, we do not do that. Yeah, but it could be a problem for sure. Yeah.
Thank you.
Thank you very much. For the sake of time, I think maybe we move to the next speaker and we can, I'm pretty sure there will be a lot of discussions.